Okay, so in today's lecture, we're going to see how to do the second stage for the universal relation composed with universal relation lower bound. So a quick recap. So we divided this argument into two stages, first parts: first stage cleanup and the second stage. In first stage, we carefully chose a transcript pi of length m minus order square root m, such that we had this set of inputs s pi, uh, which we visualize as a two-layer tree. So every pair of input here is a matrix vector pair. So a leaf here corresponds to an input x1 a1. This is to x input x1 a2, and these inputs are the inputs which can be given to both Alice and Bob, and then you would reach the node pi. And we had this additional guarantee that in the first stage, players learned at most m minus order square root m bits about the matrix, and at most m minus order square root m bits about the vectors. And this was done by ensuring that the number of matrices only decreases by that factor, the factor that is related to communication. So it halves for every bit of communication, and the number of vectors for every matrix that we consider also only half for every bit of communication. So at the end of the first stage, we have these two guarantees, and using these guarantees and using this average degree of a row as a measure of information, we were able to do this following cleanup. So what did this cleanup do? It took this fairly large set S pi and did some pruning. It deleted some matrices and all of its vectors altogether, and and in the remaining matrices, it deleted some of the vectors during the pruning process, and at the end of the pruning, whatever matrix survived, it had at least two vectors associated with it. And we, at the end of all this pruning, we discard all but two vectors associated with the matrix and call one of them A of that matrix and the other one the P of that matrix. So, and what was the guarantee on this set? So this set, again, this S dash pi can be thought of as two things. So S dash pi is a layered set. It's a set of matrices and a set of vectors associated with that matrix. And by the properties of cleanup, we had this thing for X dash, this set of matrices X dash, we had a bunch of revealed rows. So these are the rows where players learned more than tau bits of information. And we saw this nice fact that I is at most m minus square root m divided by tau, where tau is the threshold, and we set tau to be square root m to make life easier. So the number of revealed rows were about like square root m bits, and we had the following properties. The first one was that everything apart from these rows are a unrevealed row. So that means, according to our measure of information, which is average degree, if you look into this set X dash, the average degree of X, this row J, which is outside the set of revealed rows, is at least 2 to the n minus tau. And remember that tau is said to be square root m. And we had this additional thing that for every matrix X and X, we kept a vector for Alice and a vector for Bob. And we also observed from just the simple rectangular property of deterministic protocols that if you give xax to Alice and xbx to Bob, it reaches the node pi. So if you start this protocol with an input of the form xax given to Alice and xbx given to Bob, it would reach this point. So at this point, promise 1 is kept on these kind of inputs. Promise 1 is kept, which said that the vectors that the players have are all they are different vectors. Ax is not equal to bx. This is because we ensured that every matrix X had two vectors, so we choose two distinct vectors. One we gave to Alice and one we gave to Bob. Okay, and there was this additional property that that we said we can use to ensure that they do not make progress on an revealed row in the second stage in any meaningful way. And that was this thing which said that for any um, revealed row I in I, we had this fact that, and for all x in x dash, you had this fact that a of x, the Alice's vector that you give with x at index I, agreed with Bob's vector that you give it index I. In fact, it was something much stronger. So for every revealed row I, either all of these entries, I entries of all of these vectors are set to 0, or all of them are set to 1. Okay, and so this ensured that so this will, we'll see in a minute that this will ensure that players have to find a bit of difference in an unrevealed row. Okay, so these are the properties that we have for this set SPy. And now we want, what do we want to do? We as the adversary want to continue finding a transcript for the second stage bit by bit, so that at the end of, like, if they are allowed to communicate not too much, if they're only allowed to communicate an additional at most n minus log m bits, we want to say that the protocol would make an error. Okay, so the way we found SPy was to, like, ensure that we have maximum number of matrices and vectors that can be given to both the players. In this set x dash, we have already broken the symmetry between the vectors. We ensured that the vectors Alice and Bob get a different. So we are trying to make sure that maximum number of matrices that can be given to both Alice and Bob remain. So basically, like, at end of second stage, we are analyzing. So this is the first stage. We got some pi, and we're going to, our task is to run the protocol for another n minus order log m bits and find another transcript. Let me denote this in green, some transcript pi dash. So this would end in a leaf, right? Because our protocol, we assume that the protocol is very efficient, so it indeed it doesn't take more than m plus n. So m minus, so this part was m minus order square root m, and this is n minus order log m, and we assume that the communication complexity of the protocol is smaller than this. So after these many bits of communication, we would have reached a leaf of the protocol, and we want to make sure that we choose this leaf carefully enough so that the protocol makes an error on this leaf. Okay, this is how we would prove the lower part. We would say that any protocol that is too efficient would make an error. Now in this parts, just saying that we were giving the same vector and matrix pairs to both Alice and Bob. So there was no way in the first m minus square root m bits of communication they could have found a bit of difference either in their vectors or in their matrices. But at this point, we can assume that they have found a bit of difference in their corresponding vectors. So they have xax, and we are running the we are going to analyze the protocol on these kind of inputs where they know that ax is different from bx. So note that the set s dash that we carefully crafted using this cleanup is not all the set of inputs that are associated with pi, right? So it has many more inputs. It's just that we are focusing on these inputs that are in the rectangle of pi. So to prove that the protocol makes an error, maybe we can use the rectangle property again and find something outside s dash and say that, okay, on that input there is a problem. But right now we would restrict our analysis to these inputs. But whenever we have these inputs, we can always remember that we can use the rectangle property to find more inputs which are supported by a transcript but not necessarily in the set that we are considering. Okay, so a simple example of that would be that, so if if there are two matrices, then we have xax. So if we run the protocol with xax, right, and xbx, we know that it would reach pi. And if we run the protocol with yax, sorry, not yax, so with y we would just give it its vector yay and yby, we would reach pi. And the simple rectangle property would tell that xax and yby is also in the, sorry, that should be a yby is also in the rectangle of pi. Note that this is not a kind of input that is inside S dash. So this is saying, uh, so there's always possibility to like look outside the current set, but we would use this set as a uh, guiding principle to find this second stage transcript. So what is the idea here? We want, so in the second stage, so we in the naive protocol, what do? In the first m bits, they find a bit of difference between a and b. So let's call that index I, and they know that ai is different from bi. Ai is not equal to bi. And then what do they know? They also know from promise 2 that in that case xi is not equal to yi, and they use the next n bits to try and figure out an index j such that xij is not equal to yij. So the goal, so we think that we assume that they're trying to find such a difference in the matrix in the second stage, and we want to delay finding such an index as long as possible. That's why we are looking at the set s dash. On this set s dash, they cannot find such a difference, right? There is, so on these kind of inputs, there does not exist ij such that this xij is different from Bob's Alice's input is different from Bob's input on ij, because Alice and Bob are getting the same input, which is x. In this case, Alice gets x, Bob gets x, so they cannot find, as long as they have inputs of this kind, they cannot for sure find an index ij where their matrices are guaranteed to be different. Okay, so we are delaying their progress for the another n minus order log n bits as much as possible. So, but there is a small caveat. So we can't really run it for n minus orders log m. So this order log m is because of some analysis that we need to end. We will also need to do an extra minus square root m. Why is that? So remember that at the end of first and after the cleanup, we claim that they have to find a bit of difference in an unrevealed row. But in an unrevealed row from the cleanup, we have the guarantee that we have is that players know at most square root m bits of information, right? So it is possible that in an unrevealed row they already know square root m bits of information, and it is possible that they can use the square root m bits of information to make and these square root m bits of information came from the first stage. So, and in the first stage we gave them the same matrices, so they possibly know that these square root m bits of information, like square root m bits of row, are same for Alice and Bob. It's possible, right? So then we can only hope to run the second stage for another n minus square root of bits, right? So just what I'm saying is that in an unrevealed row, it could be that the players have learned that the first square root of bits of this row are the same for Alice and Bob. So in the second stage, they only need to look for a difference in this n minus square root m bits remaining in the vector. So remember that each row of the matrix is n bits, right? So because of the threshold that we chose, we can only run the second stage for n minus square root m bits. So in general, if this was a tau, we could only run it for n minus tau bits, because it is possible that on some row which they are focusing, we have narrowed their search space to just as much. Okay, so we'll take this additional hit, but it's not too big because it'll just get added to this order square root term. We are already losing this order square root term in the first case, so it's another like, so we had something like 4 square root term, it will become 5 square root term. So it's not a big deal because we are losing something in the first stage itself. Okay. So, and now we'll see how to build the second stage transcript. Goal, build second stage transcript. This is actually fairly straightforward. Pi dash. So we are at this first stage transcript pi, and we want to go down, and I think I use green, go down to a leaf, pi dash. So this is a leaf. So what do we do? So we look at, so let's say this node is a node held by Alice. So what does Alice do? So there is like Alice divides her input into like 2 parts. So maybe on 0 she sends it here, and on 1 she sends it to this node. So now as we have seen already, we are not looking at all possible set of inputs, we are just looking at S dash, right? What is S dash? I think I called it S pi dash here, but it's S dash. Let's simplify our lives, let's call it S dash. So S dash is this set of matrices X dash and this bunch of vectors for every matrix, right? I want to see how S dash gets divided by Alice. So just to say, S dash, let's call it pi, is a set where I had a bunch of matrices x1, x2, let's say xp, and for every x I have ax and bx, right? So this is x2, so this will be ax2, will be bx2, so on and so forth. This will be axl and this would be bxl. So, and now as we discussed earlier, we are going to run the second stage on inputs where Alice gets some matrix from here and the vector and the corresponding a vector, and Bob gets the same matrix but the corresponding b vector. So we should first of all we'll take one input of that kind and we'll analyze what the protocol is. So we'll give let's say x2 to Alice and x2 bx2 to Bob, right? So we are going to analyze the behavior of the protocol on these kind of inputs. So uh, maybe on this input Alice sends 0, so this ends up here, and maybe on some other input like let's say this is like x3 ax3 versus x3 bx3, Alice sends it here. So this input ends up here and this input ends up here. So you can look at entire S dash pi and you can divide these inputs into 0 and 1, right? And how do we so how does the labeling go? It's not on the, so earlier we did a labeling on the leaf, right? So how did we do the labeling? Because we gave, so once in the first stage, what did we do? We chose a matrix and we just chose one of the vectors and we gave both the matrix and the vector to both Alice and Bob. So by describing one pair of a pair of matrix and input, we could describe the entire inputs to Alice and Bob. But here it's slightly different. So here because we have fixed for every matrix, we know what vectors we are going to give to Alice and Bob. Giving a matrix and understanding this as HSS dash itself tells you what the behavior of the protocol is going to be, right? So yeah, so for example, so here we will label this, so we just need to label the matrices. So we will label this matrix with 0, and for example, if I had the x3 matrix here, or let me just make my life simple and say that this last one xl axl versus xl bxl, if we give this, then Alice sends 1. In that case, I would label this one as 1. So I can label, so by the next message of Alice, I can say a matrix is either label 0 or 1. How do I do that? I just take that matrix and give xax to Alice and xbx to Bob and see what Alice says on that particular input. Okay, so the next message of Alice divides the set x dash, so we call this set x dash, right? So it partitions the set x dash into two parts. 0 where on this input, on this specifically constructed input, Alice would have said 0, and on 1 where Alice would have said 1. Are there any questions about this labeling? So earlier here we can label a matrix because once we choose a matrix, we are always going to give the A vector to Alice and B vector to Bob, and there are no other vectors that we consider. Okay, so a matrix describes the complete input to the protocol. So you can tell what the protocol does next on this input. Okay, and what do we want to do? We want to be able to give the same matrix to both Alice and Bob in the second stage as long as possible. So what's a clever idea? So should we go to 0 or should we go to 1? Let's say the majority of the x's are labeled 0. Where do you think we should go? We should go to 0. So what are we going to do? So the next bit is going to be 0 if majority of the x's, majority x in x dash gets uh, gets labeled 0 and 1 otherwise. So this ensures that so we go from s dash pi to s dash pi dot 0 if majority. So we go to this node, we'll go to this node if majority of x in x dash gets the node 0, and here if majority of them get 1. But in doing so, what would we have ensured? Like, okay, so what Alice is doing is that she's dividing x into two parts, sorry, x dash into two parts. One is x dash 0 and x dash 1. We know that one of them would be at least half the size of the original, right? Because x dash is partitioned into two sets. This is an induced partition. So what is actually getting partitioned is like the inputs of Alice, but because we have chosen the inputs this way, this induces a partition of the matrices as we saw earlier. So this says that because it's so, then there exists some next bit which is in 0 1 such that x dash b is at least x dash by 2. So what does it mean? It means that the number of matrices that we can give to both the players remains at least half what we had earlier. So remember, x dash is that special set that we got from cleanup, and we will go to the next bit where we can retain half of these matrices, at least half of these matrices. Maybe we'll retain something more. So, and we do this so on and so forth. So x dash gets goes into x dash 0. Note that this also describes a set s dash pi dot 0. So just to think of this picture, so we had this partial transcript pi, and the next bit of the protocol is either 0 or 1. We chose 0 because majority of the matrices got labeled 0. So we are saying that, okay, so we are currently in this part. So we are extending this first stage transcript bit by bit until we reach a leaf. So, and by looking at these matrices, we know what's s dash pi 0, right? So this x dash 0 is a subset of x dash. So in x dash we had for every matrix, uh, so for every matrix in x dash, we had two special vectors, ax1 and bx1. It's an easy exercise to see that both of these are still valid inputs for Alice and Bob. So if you look at the rectangle of, let's say pi 0, in rectangle of pi 0, you would have xax and xbx for any x in x dash 0. Okay, so the way we constructed this, that's how we labeled it, right? So we labeled a matrix 0 if this particular input uh, on this particular input Alice said 0, so this is inside the rectangle of this node, and it was labeled 1 on the input Alice spoke 1, so in that case it is in this rectangle. So we have maintained this property that we are looking at this kind of very special inputs where both the players get the same matrix, but they get two different column vectors, and these vectors are determined by the cleanup stage. We have determined them to be some arbitrary but fixed vectors at the end of cleanup, and we are going to retain these vectors. And in every bit that we speak, the number of these matrices are going to go down only by a factor of 2. So we'll have like a bunch of this, I don't know, some XP, and this is at least half of the matrices in X dash. Okay, so this set is like at least X dash by 2. So now, did we have any guarantee? So earlier we said that in the first stage we said that we initially in the root of the transcript we had 2 to the mn matrices, and every time we half the number of matrices in the worst case. So after m minus square root m bits of communication, there were at least 2 to the mn divided by 2 to the m minus square root m matrices in our set. But note that at the end of cleanup, we did not make any guarantees about cardinality of X dash, right? Did we? We did not. All we did was that we said that we proved this property, that there are a bunch of unrevealed rows for this set of matrices X dash, such that all of them have like lot of information in their rows, right? In every row we have at least n minus tau bits of information. So what are we going to use here? So we won't say that, okay, after so what's the length of our second stage? The length of our second stage is exactly this number. It's this n minus order log m minus another square root m bits. So after that many bits of communication, we want to say that in every row there are quite a number of, in every unrevealed row there are quite a number of bits that are not known to both the players. So what are we going to say? So after n minus order log m minus square root m bits, so we reach some node pi dash, and we will have some set x pi dash associated with it. It would be a subset of our set x dash from the cleanup, right? So the way we are constructing this partial transcript bit by bit, the next set of matrices that we choose is going to be a subset of x dash, right? So x dash 0 is a subset, x dash 1 is a subset, and the next stage x dash 0 0 would be a subset of x dash 0, x dash 0 1 will be a subset of x dash 0 as well, so it is in turn a subset of x dash. So we are like refining the set of matrices that we had at the cleanup further and further. So whatever set of matrices that we are left with would be a subset of this original set of matrices that we started with. And what are we going to argue? So intuitively the argument is the following. So in this set x dash, so in the set x dash, there are a bunch of revealed rows. So let me just put them in red. So in this revealed rows, the players maybe they know a lot of information, but in every unrevealed row, they know only like so much information. They only like know at most square root m bits of information. And in the next n, so how did we get to x dash pi? By communicating this n minus order log m minus square root m bits. Okay, so how many bits of information could they have learned in any unrevealed row? That's quite small, right? So one in x dash pi, okay, the revealed rows we don't care about anyway, so I'll just mark them as it is. Maybe they've learned more information now, doesn't matter. Okay, the revealed rows are as such, but in the unrevealed row, they knew some bits of information. They knew like square root m bits of information, so which we had denoted in this, like in this color. We had this, and in the next n minus order log m minus square root m bits of information, maybe they use this to completely understand one specific row. But in the worst case, in any of the unrevealed rows, they could not have learned additionally more than these many bits of information, because they only spoke this much amount of information. So in any unrevealed row, how much more have they learned? They could have learned quite a lot, but they could not have learned more than what was initially there. That was square root m. So this was square root m, right? Plus this thing. So that's why we needed this minus m. So n minus order log m minus square root m. So the amount of information that they have learned is at most n minus order log m, right? So the amount of information in these rows combined from the cleanup and the second stage is only this much. So what does that mean? We had n bits of information in every unrevealed row. Sorry, n minus square root m bits of information in every row. The cleanup plus the communication only takes up n minus order log m bits. So how many bits are remaining here? We know that the players do not know about at least players don't know at least order log m bits of information, right? So in an unrevealed row, this is only about an unrevealed row. Yeah, this is fairly intuitive stuff. We're doing this kind of worst case calculation. Maybe they use this n minus order log m minus square root of bits of communication to understand one particular row. So it is possible that in that row they have learned this plus this amount of information, but even if you add all of them up, there's still order log m bits of information unknown in a unrevealed row. And this is what we are going to use to say that they could not have for sure found a bit of difference in an unrevealed row, and we have to make sure that they cannot they're sort of not finding a difference in the revealed rows. Okay, so what are we going to do? So first we will so this intuitive calculation that we did, which said that in any unrevealed row at the end of second stage there should be at least order log m bits of information that is not known to both the players. We want to show this formally. So what do we want to do? At the end of second stage, so basically remember that this is where we went from x dash pi to this x dash pi dash, right? Sorry, this is pi dash. So this pi was the first stage transcript. Yeah. So and the way we also guaranteed, we had this guarantee that x dash pi dash is at least x dash pi divided by what? So every bit of communication in the second stage, this set would half. So how many bits did we communicate? It's something like n minus order log m minus square root m, right? So we have this guarantee, and then now we want to say that so remember that associated with x dash pi we had this set of revealed rows. So we will, with x dash also we will think of them as the revealed rows. So what we intuitively argued earlier is the following formal thing. We want to prove that, okay, to prove for any row j which is an unrevealed row, so that means it's not in the set of revealed rows. So the set of rows was m and set of revealed rows was I, so this is the set of unrevealed rows. We want to say that the amount of information that the players have learned at the end of second stage, or in this set of matrices x dash pi dash, sorry, in this set of matrices x dash pi dash is still not too large. So they don't know at least order log m bits of information. So this is, and how did we measure information? We measured information as the average degree, right? We want to say that average degree of J of the set of matrices x dash pi dash, which is the set of matrices that we have at the end of second stage, is at least 2 to the order log m. So if we had if a row had average degree n minus tau, that meant that so if a row had average degree, n minus tau, this meant that the players don't know at least n minus tau bits about that row, right? And what we wanted to say by this intuitive calculation is that at the end of second stage, they don't know at least order log m bits. So what this is in turn equivalent to saying that every unrevealed row at the end of second stage, so this is the end of second stage, this is the set at the end of second stage, every unrevealed row at this point has average degree at least this much. Okay, so this is what we want to prove. If we prove this, it's fairly straightforward to complete the lower bound. So how do we prove this? So this is something, okay, so to understand this, we need to understand, so we have no handle on the average degree of this set, right? But we have some handle on the average degree of x dash pi. So we know, so what do we already know? So we know that average degree j of x dash pi, which is the cleaned up thing from the first stage, was at least 2 to the n minus square root m. And now you kind of get the picture, right? What we want to say is, I said, okay, this set got halved for these many times. So we want to say that every time a set gets halved, the average degree also at most gets halved. So if we can prove that after these many bits of communication, so this is what I'm trying to claim. This is like an intuitive statement. Prove every time a set of matrices gets halved, the average degree in the new set is at least half the original. Okay, if you believe this intuitive statement, what can we say? We knew that for every bit of communication, how did we choose? We choose the next bit by ensuring that we kept at least half the matrices, right? So after n minus, so this is why we could say that the number of matrices at the end of second stage is at least the original set of matrices divided by this factor. So, and we knew that there originally we had average degree 2 to the n minus square root m, and for every bit of communication we would half this. So this would prove that this is at least, so at end of second stage this is at least n minus order log m minus square root m, and if you cancel things out, what do you get? You get this is at least 2 to the order log m, and this is what we want to prove. Okay, so let's prove this intuitive statement formally. So what am I claiming? So this is, let me call this a lemma. So x and so x is a subset of matrices, and x dash is a subset of x. It's a, so if you have a collection of matrices x, and you have a sub collection of that collection with, let's call that x dash, with the guarantee that x dash is at least x by 2. Then I claim that average degree, and then for any row j in M, we have M rows, right? The average degree j in x dash. Oops, this should all be curly x's. So whenever we have a collection, I should have been writing curly x. Hope you understand. I hope I did not mislead you with the capital X. So this, the average degree, is at least half the average degree j in, oops, I need a bit more space. So let me just make some more space. This is at least half the average degree j in x. Okay, this is what we want to prove. This is what we intuitively said earlier. Every time a set of matrices get halved, the average degree halves, and if we have this, we know that this can be proved, right? This is an easy statement to do. So how do we prove this? So what is average degree j of x dash? So remember this graph. So we had this graph where you had all the partial matrices with the row j removed here, and all the partial matrices with just the row j from x dash here. This was, and the average degree was the number of vertices on the left side divided by the number of edges, or equivalently the number of edges is x dash. So there's an edge if this completed matrix is in x dash, right? So the number of edges is x dash, and the number of vertices on the left hand side is x dash minus j. Okay, now what do? We need to somehow relate it to average degree of x. So we need to somehow bring in x. What did we know from the assumption of the theorem? So let me just erase this picture. I hope you understood this. So from the statement of the theorem, we know that x dash is not too small compared to x, right? So we know that x dash is at least x by 2. So this is saying that this is at least x by 2 x dash minus j. Okay, are we done? Not really. Like now we need to somehow relate it to average degree j of x, right? But we have x dash minus j. But can we say something about the relation between x dash minus j and x minus j? Not really. From this relation we have this relation, but that doesn't really tell us much. But we know that the set of patterns that you get from dropping the jth row in a subset of matrices, this cannot be more, this is a proper subset of the patterns you would get from dropping it from a larger set of matrices. This is a trivial game. So what I'm saying is that, okay, if you have 3 matrices and you remove 2 the row 1 from all 3 of them, and the set of partial matrices that you get cannot be smaller than, let's say you take the first 2 of them and then removing the first row. So if you have, if, so this is the claim, this is, maybe I can just write it as a simple claim. Claim says that, so if x dash is subset of x, then x dash minus j is a subset of x minus j. It's just a simplest claim that there is, right? You have a bunch of matrices. It's just by definition, you have a bunch of matrices, you remove the jth row and you look at the partial matrices that you get. That will be a superset of, if you had done this procedure to a subset of the matrices, right? You take a subset of these matrices and you remove the jth row, you're not going to get any new pattern, right? This could be, in fact, you can imagine scenarios where they are the same. Like for example, we could we could have this thing where we are dropping the first row, and the set of matrices that we have is like 0 0 1 1, 0 0 1 0, 0 0 0 1, and 0 0 0 0. Let's say my set x is this, right? this is my set of matrices, and let's say my set x dash, okay, there's a dot here, should be, so set x dash is just sum 2 of them, and this is a bunch of subsets that satisfy this hypothesis, like this assumption that we had, that x dash is at least x by 2. But if you look at x minus 1, what is x minus 1? So sorry, x minus 2. What is x minus 2? If I drop the second row from this set of matrices, it's just one pattern, right? It's just 0 0. And what is x dash minus 2? That is also just 0 0. It is possible that these two things are equal, but this one is always a subset of this one, right? So if you drop this any row from here, the patterns that you get is a subset of the patterns you get by dropping any row. So this claim is like trivial. So once we have this claim, then we know that cardinality of x dash j is less than or equal to cardinality of x minus j. So then if you substitute x minus j here, this can only decrease this quantity, right? If you increase the denominator, the total value only decreases. So I can say that this is at least cardinality of x divided by 2 times cardinality of x minus j, just by this equation. And what is this? This is by definition the average degree j of x. So this completes the proof, because this quantity here is just this one, and the half gets carried over as well. This is this half. Yeah. Are there any questions about this theorem? Let's lemma. I hope this is clear to you. So this says that this captures that intuition that we had. If they speak an additional some k bits of information, that cannot increase the amount of information in any row by more than k bits. Here we are only going to use this strategy on the unrevealed rows, but this is in general true if you had, like, if you knew something like L bits of information here and you spoke k bits of information here, after this you would know at most L plus k bits of information. Okay, so this was just a formal way of capturing this intuition. So this measure of information is important for all these reasons. Okay, so this says that, okay, so this completes a proof that and now we just apply this lemma, and then we get that average degree j of x dash pi should be at least, so what do we know? It's at, so this is half these many times, so average degree j of this thing is at least 1 over 2 to the n minus order log m minus square root m of the average degree of x dash pi, which was 2 to the n minus square root m. So if you cancel everything out, you get this one. Okay. So what do we have at the end of second stage? So just to summarize, at the end of second stage, we have two things. So we had an initial transcript of length m minus square root m order square root m bits, which we called pi, and then we extended this into the second stage and found another leaf of this protocol. Let's call that pi dash, and we had a set x pi dash associated with this thing. So what was the thing? Like, if so, these are the set of matrices, and then associated with the set of matrices we had a bunch of vectors. So we had the set s pi dash, which looked as follows. You have a bunch of matrices, which is x pi dash, and so this set, we call this x pi dash, and with these matrices we were always giving the following vectors to Alice and Bob. Alice gets the vector ax1, Bob gets the vector bx1. These vectors are from the cleanup. We did not remove any vectors during the second stage. So for every matrix, there are exactly 2 vectors associated with it, and so on and so forth, xr, bxr. And then we have this additional property. So we just proved that property for any unrevealed row. So for any j in m minus I, remember the definition of unrevealed row is from the cleanup and the first stage. The unrevealed rows do not change during the second stage. For any such thing, for any unrevealed row, we know that average degree inside this set x pi dash is at least 2 to the order log m. So I did not specify this constant, but we can fix it to be something very soon. Okay, so this is the thing. And now we want to show that, okay, so what's our goal? Let me just make this somewhat smaller so I can just complete the argument in this page itself. So just shrink this. I hope you can still see this. Please let me know otherwise. Okay, so now what do we want to show? We want to show that goal, prove that pi dash s. So this is much easier to prove in the non-promise version. So remember in the non-promise, so let me just briefly remind you what the promise version was of the universal composition of universal relation. So this was this problem where Alice gets xa and Bob gets yb, and the goal is obviously to find an ij such that xij is not equal to yij if the following promises hold. So if the first promise is that a is not equal to b, and the promise 2 was that if we could find a bit of difference in the vectors, then there should be a bit of difference in the columns. So it said that for all I such that ai is not equal to bi, this implies that xi is not equal to yi. So we can consider the non-promise version where they might get inputs which do not have this promise, and in that case they can output perp. So this is one option, and can output perp if either promise 1 or promise 2 or a combination of them is broken. It's not true. So let's consider the non-promise version and then prove that in the non-promise version the leaf node pi dash is an error node. Okay, so how do we do that? So clearly anything inside this set x pi dash, this matrix can be given to both Alice and Bob, right? So here, so if I run this entire protocol, this protocol was called pi, right? If I run the entire protocol on some x that is here, let's take x1 itself. So if I run the protocol on x1 a x1 and x2, sorry, not x2 but x1 b x1, could they have found a difference? Could they have found an index like this? Could they have found it ij where xij is not equal to yij? No, because what is x and y? X and y are the same matrix x1. So there's no way they can output an index ij and be correct. So their only option here is, because okay, so this leads to the node pi dash. So this is in the rectangle of pi dash. So at pi dash they have to output perp, right? So remember that if either promise 1 or promise 2 is broken, it's not necessary that they have to output perp. but they can output perp only if these promises are broken. But in this carefully chosen set of inputs, there is no other option for them, right? So obviously promise 2 is broken because ax is different from ax1 is different from bx1, and so there's some index I where ax1 is different from bx1, but on that index the corresponding rows of Alice and Bob are the same, so promise 2 is broken. But that doesn't necessarily mean that they have to output perp, but here that's the only option they have, because the other option would have been to find an index ij that differentiates Alice's matrix from Bob's matrix, but that's impossible because Alice and Bob got the same matrix. And this would be a problem, and we saw that, okay, at pi dash, then the protocol has to say I give up, reject. And now to prove that the protocol errs, we have to like conjure some other set of inputs that are supported by pi dash, on which they cannot output perp. So right, so now to complete the proof, the lower bound will show that there exists some xa comma yb supported by the rectangle of pi. It is not necessarily from the adversarial input set that we considered, but then using the rectangle property, we saw that whenever we have a set of inputs, we also have some additional set of inputs. So from maybe like this additional set of inputs, we will find this xa and yb such that we're going to ensure that promise 1 is true and promise 2 is true. And in the case that promise 1 and promise 2 is true, the protocol is not allowed to output perp, right? So if they have a set of inputs, if so because this is a deterministic protocol, this node pi, without looking the specific input that it has in its rectangle, it has to say either perp or it has to say ij. We already claimed that it cannot say ij because there's some set of inputs where there is no ij, so it has to output perp. Now we will checkmate it by saying that it cannot output perp also. There is some set of inputs where they have to output ij. Okay, and this would complete the argument. This would say that there is no consistent labeling for the rectangle of pi. So if we prove this with the earlier statement, it says that pi dash has to output perp, and this says that pi dash cannot output perp, and this means that there is no labeling pi dash that works. And this implies that because we are a deterministic protocol, we have to, at every leaf, we have to evaluate, we have to give an answer to the relation that we are solving. So we have to like either say perp or give some ij, but in this case there's no one answer that works. So this means that the protocol that we started with makes an error. So to complete the lower bound, now it's enough to show an input xa and yb in the rectangle of pi dash where the promise 1 is true and the promise 2 is true. If just to recall, promise 1 says that the matrices are different, and the promise 2 says that ai bi are different. Okay, so how are we going to do this? So we are going to do the following thing. Remember that the set of matrices that we have at the end of second stage, which we called x dash pi dash, and then we have a bunch of the inputs associated with it. So we think of this set as the following, right? We think of it as a 2-layer tree. So we have epsilon, just a thing, and bunch of matrices x1, x2 up to xr, and for each matrix we have two specific inputs, ax1 and bx1. ax1 is given to Alice, bx1 is given to Bob, bx2. So how are we going to construct this x and y? So we are going to show that we want to show that there is some input like this in the rectangle of pi which satisfy all these promises. We will not be able to construct this in a very constructive manner. What we are going to do is we are going to employ a probabilistic argument which would sample a matrix xa and yb in a way that will show that with non-zero probability we will get an xa and yb that satisfies all these properties. So first it's in the rectangle of pi dash, and second promise 1 is true, third promise 2 is true. So if we have a sampling procedure which returns these things with a non-zero probability, that means in the rectangle of pi dash there should be at least one such input, right? And that would complete the proof. So we are not going to explicitly describe xa and yp. What we are going to do, we are going to use a probabilistic argument which would say that if we sample this matrix vector pairs in this certain way, we will have non-zero probability of satisfying all these properties. So whenever an event has a non-zero probability, that means there should be at least one such thing in your universe. So this there exists statement is true. It's a fairly standard argument, right? Any questions about this whole strategy? So what we want to, like, to complete the proof, we want to come up with this. We will describe a randomized algorithm that samples something that's with non-zero probability, and that would show that there exists such an input, right? Okay, so what is our sampling algorithm going to be? Okay, so we first choose x1 to be a choose x1 uniformly at random. So maybe not, let's call it x1, let's call it x. Choose x uniformly at random from the set of matrices that we have, which is x dash pi dash. So like there are, I don't know how many matrices are there, but I choose any of them with equally the same probability. So I'll choose this one. So if there are r of them, I choose one of them with probability 1 over r. And now we are going to sample with repetition. We don't know what x is. And again, we will make another a uniform sample. Let's call that matrix y. Y uniformly at random from x dash pi dash. So now it's, so this is with repetition. So it is possible, so because we are doing with repetition, it is possible that x is equal to y, right? And there's a 1 over r square chance of this being true, but nonetheless. So this is our sampling algorithm. This tells how to get the matrix part, and how do we get the vectors. So we got two matrices. So maybe one of them we'll give it to Alice and one of them we'll give it to Bob, but then we also need to give the vectors to both Alice and Bob. So what do? We don't have to do any randomization anymore. So once we have this matrices, we know what. So for every matrix, there are exactly two vectors associated with that matrix, and one of them is designated for Alice and one of them is designated for Bob. So just let me do this shrinking trick so that I can just complete the sampling algorithm. And now what are we going to do? So give Alice x comma ax. So with every matrix x that is in x dash pi, there's a unique vector ax that is the vector that we assume that we will give it to Alice. So give that to Alice. And what do we do for Bob? It's analogous thing. We give y comma by to Bob. Okay. Okay, so then we need to like analyze with what probability will satisfy property 1, property 2, and what probability with this will be in the rectangle of pi dash. So the first thing is easy to do. So is it clear how we got xax and yby? Yeah. Okay. Right. Yes. Take that silence for a yes. But please ask me questions if you have any. So this it is clear. So first thing is easy to say that XAX and YBY is in the rectangle of this input is in the rectangle of pi dash. Why so? Because XAX XBX is in the rectangle. So this input is in the rectangle, and so is YBY comma YBY, and the rectangle property says that you can take this one and this one and you'll get an input that is in the rectangle, right? So you take XAX from here and YBY from the Bob's side, you get an input which is also in the rectangle. So that this sampling procedure always satisfies this property that we are in this rectangle. Okay, so this is always satisfied. This is with probability 1. This is true. This is just basic use of rectangle property. Now I want to understand with what probability that promise 1 is true. So we knew that promise 1 is true for a particular matrix X. So we knew that for any X in X dash pi dash, we knew that AX is different from BX. But it is possible that for some X and Y which are possibly different, AX is equal to BY. So we want to ensure that the promise 2, like the promise 1, is also universally true without any problem. Like we want to show the promise 2 is also like always true. So how do we do that? So to do something like that, again we will use another probabilistic argument. So what are we going to do? So we will not run the sampling algorithm on this set X dash pi, but we'll do some more modification to this set X dash pi. So let me call this set X dash pi as X dash, just X dash. So I guess I used it I used X dash to denote something at the beginning of the protocol. So maybe let me call this yeah, this is getting ugly. Let me call this X tilde. Okay. So before running this sampling algorithm, I would reduce the set of inputs that we have at the second stage to be even smaller. So we have completed the second stage. We are at a leaf. We are looking at these inputs, but then we can do the following thing. But we saw that on these inputs, we don't always know that promise 1 is true if we sample in this way, but we want to make sure that we go to a smaller set of inputs where the promise 1 is always true. So what are we going to do? What did promise 1 say? That like this A vector and this B vector should be different for any input that you consider, right? So again, what are we going to do? So yeah, so we will do the following thing. So we want to partition. So we want to say that these vectors are partitioned into two parts such that these are all vectors from 0 1 to the m, right? So I want to partition 0 1 these vectors from 0 1 to the m into two parts so that I know all the vectors that Alice get, all the AX for any X and XR is from one part of the partition and BX is from another part of the partition. So this way I would know that like no matter what X and Y are, if X and Y are the same, then already we know that AX and BX are different. But if X and Y are different, so say for example, like if we sample this to be X and this to be Y, we can guarantee that these two things are different. So why is that? How do we do that? So we first randomly partition these matrices. So how do you randomly partition these matrices? You just think of like giving them as labels from 0 and 1. right? You want to partition them into two parts. So you label every matrix, no matter whether it's an every vector into two parts. So no matter whether it's an A vector or a B vector, you just randomly label it either 0 or 1. So with probability half, it would be labeled 0, and probability half, it will be labeled 1, right? And now I want to think of the following event. So I want to like, so this is also 0 1, this is also 0 1. So I want to understand with what probability Alice's input, so the partition that Alice's input goes to is different from the partition that Bob's input goes to. So I want to understand for any x in x, uh, I call this x tilde, so this set I call it x tilde. Oops. So for any x in x tilde, what is the probability that ax, so the label of ax is 0, or I don't care if it's 0 or not, label of ax is different from label of bx. So this is equivalent to saying that ax and bx went into two different parts, right? Either ax went into 0 and bx went into 1, or bx went into 0 and ax went into 1. So what is the probability this would happen for a particular x in x dash? Because this is going to be 0 with probability half, and this is going to be 1 with 0 with probability half, the possibility that they are equal is what? So either they get 0 0. So if this is not the case, actually this event is also easy to analyze. So what are the possible events? So the labels are either 0 0 0 1 1 0 1 1. So what's the probability that label is this thing? It's half times half, which is 1/4. It's the label, this thing is 1/4, this is 1/4, and this is 1/4. And what's the so in this is our probability space of label of ax and label of bx, and we are choosing like any one of them is equally likely. So, and we are looking at this event. What is this event? It says that label of A is different from label of B. So what is that subset of the universe that you're looking at? It's just this. So what's the probability of this happening? That's 1/4 plus 1/4, which is half. And this is, yeah. So this says that with half probability for a particular x, the label of x would be, label of ax would be different from label of bx. Or you could think of it as like dividing. So if we don't think of it as a and b, and just think of this as a set of vectors, so let me call this set A, which is a subset of 0 1 to the m. This set A is so with this randomized procedure, this set A is getting partitioned into A0 and A1. And now we are analyzing that if we choose A0 A1 uniformly at random in this manner, what is the probability that for a particular x, the labels are different for its vectors of Alice, right? It's Alice vector and it's Bob vector. So on expectation, so now we want to say that okay, so we know that with probability half this would happen. So on expectation, how many matrices would be there where the label of Alice and label of Bob is different? Or in fact, if you think of it this way, label of Alice goes into one partition of 0 1 to the m, and label of Bob goes into the other partition. So how many matrices are there on expectation where this would happen? So so that is just half times the number of matrices, right? So probability that this event would happen is half, and just by the linearity of expectation, you know that. So this is what am I claiming? So the number of matrices, so the expected number of matrices x where label of ax is not equal to label of bx. What is this? It's the total, it's just expectation of this summation of xi, where xi is an indicator random variable telling you that if this event happened for this matrix x or not, right? I mean, let me not call it xi, sorry, let's call this 1x. So it's an indicator random variable telling whether this happened for this matrix or not. So you just sum it over all x and x tilde. So by linearity of expectation, you can take the summation outside, and it's just summation over all x and x tilde, expectation of this indicator random variable. What is the expectation of this? With half it's 1, with half it's 0, so the expectation is just half. So the expected number of matrices where this would happen is just so this is equal to half times x tilde, the total number of matrices. So again, so this says that if we partition the set of matrices, set of vectors uniformly at random into two parts in this following way, uh, on expectation, half of the matrices in your set would would have this property that their Alice vector is from the first partition that you have, and the Bob vector is from the second partition, like it's from a different partition. So Alice, the partition that Alice vector goes into is different from the partition that Bob's vector goes into. So because the expectation, on expectation this happens, there should be at least one event, since the expected number of matrices were x, which is in x tilde, where L of ax is different from L of bx, is at least cardinality of, it's exactly cardinality of x tilde by 2. There exists a partition, let's call it A0, A1, such that under this partition there should be at least one event which witnesses this expectation, right? So under this partition, or which is that like equivalently, so this is equivalently a labeling of 0 1 to the m into two labels, right? It's either 0 or 1. So under this partition, for all so at least half of x in x tilde have label of ax is different from label of bx. So by this, just by this simple analysis, we know that there exists some subset. This is why I said the notation is getting uglier by the minute. X tilde tilde subset of x tilde, where x tilde tilde is at least half x tilde by 2. So just to summarize, what did we have? We had some bunch of matrices, and by removing half of these matrices, so there is some partition of the vectors into A0 and E1, so that we may lose half the matrices, but there are at least half the matrices where Alice's inputs come from one partition and Bob's inputs come from the other partition. So now we could run the sampling algorithm on x tilde tilde. So remember, this was x tilde, and instead of x tilde, we'll run it on x tilde tilde. Ax and bx are defined similarly, like it's the same ax and bx that you would get from x tilde, right? So if you sample this way, if you sample from the set x tilde tilde, what do we have? This additional, we get this additional property that ax comes from a0 and by comes from a1, right? And we know that, like, no matter whether irrespective of, so this was a global partitioning, right? Irrespective of x equal to y or not, we know that all the Alice's vectors come from A0 and all the Bob's vectors come from A1, right? This was very important. Why did we do this? This was a global partitioning independent of the matrix. So the partitioning did not depend on the matrix. The partitioning was global. So we just forgot about the matrices for a while, and we just labeled the matrix, the vectors that are associated with these matrices uniformly at random. Oh, so an important thing to remember here is that, so this picture is slightly misleading. So maybe this vector is 1 to the m, and maybe this vector is also 1 to the m. in that case we won't sample its label twice. So we are just sampling a labeling for 0 1 to the m. So we will either put the label of 1 to the m1 as 1 or 0, and if it is 1 then we will keep it to be 1 here and here as well. So maybe this picture was slightly misleading because there could be repetitions here. So I think of this as a flat set. So like I don't care about the repetitions among these vectors. I think of these vectors as coming from the subsets of as just m-bit Boolean vectors. And for every unique vector that I see, I choose a random labeling. So the partition that we get is independent of where they appear in this tree, right? So the part label of 1 to the m does not depend whether 1 to the m was a child of xr or x1, or whether it was being given to Alice or whether it was given to Bob. So this partitioning is uniform, it's universal, and based on this partitioning we get some labels for the matrices, and this says that at least half of the matrices would see things which are coming from two parts. And so because this partitioning A0 A1 was independent of x and y, we get that always oh sorry, I can't say that always ax is from A0 and always by is from A1. All I can say is that like ax comes from A0 and by comes from A1, or ax comes from A1, in that case by comes from A0. They do not belong to the same partition. But the moment they do not belong to the same partition of 0 to the m, they are different vectors, right? A vector cannot get two parts. Like these are all the possible vectors, and we partition them into the 0 part and the 1 part. So this either comes from here or there, but based on where that is, the other one comes from the other part. Okay, so by this sampling algorithm we actually satisfy this addition. So I see that already like 4 minutes over time. I'll wrap it up in another 3 to 4 minutes if that's okay with everyone. Also, if you have some other engagement, you can leave and I'll try to upload this soon to YouTube. So we can also ensure that property 1 is true. So the way we sample x and y, so the xax would be different. Xax, so we sampled xax and y by, and we are guaranteed that ax is different from by. So by this sampling algorithm, this input would be in the rectangle of pi dash, and the promise one which said that Alice's vector is different from Bob's vector is also always true. But in that process we lost about half the matrices in the set x pi dash. So this could reduce average degree a bit, but how much could it reduce by? This lemma says that whenever you reduce a set of matrices by half, the average degree only goes down by a half. And what sort of average degree guarantee that we had? We had it was 2 to the order log m. So now we might not have this. We would get 2 to the order log m by 2, which is 2 to the order log m minus 1. So I can take that minus 1 into my order notation. So it's still 2 to the order log m. So what am I saying? Even for, so we are not looking at all of x tilde. So we knew that average degree so for any j in m minus I, average degree j of xj, x tilde j was at least 2 to the order log m. But now I'm looking at x tilde tilde, which is at least such that x tilde tilde is at least x tilde by 2. Why did we go to this? So that we could always ensure promise 1 is true. We had this partitioning, and this ensured that these come from two different parts, and ax is not equal to by for any x and y, if x and y are same or not. So we had to go to this. So in that thing, by the lemma we proved, what do we have? The average degree is still x tilde j, sorry, there should not be a j here. This is for a set of matrices, and j is the row number. So the x tilde is at least 2 to the order log m minus 1. So I'll forget about this minus 1, I'll just absorb it into the order notation. Okay. So now I need to prove with what, so I want to prove that with non-zero probability promise 2 is also true. So to complete the argument, prove that with non-zero probability promise 2 is true. So what is promise 2? Promise 2 said that for all I in M, if AI is not equal to BI, it implies that Xi is not equal to YI. So now you can see that I don't have to ensure promise 2 for any of the revealed rows, right? So for any revealed row, so for all I in I, so for any revealed row, we knew that for all X comma Y in X tilde tilde or X tilde, we knew that AX I is equal to BXI. So the promise 2 doesn't even kick in this case, right? Because these indices are same for all the revealed rows. So on the revealed rows, I don't have to ensure that they are the same. They are different. So this is why I said, like, if I maintained this property, then I don't have to worry about revealed rows. I just need to worry about unrevealed rows. Okay. So now what do we need to show? We need to show that if this is true for some unrevealed row, if there is an I, so the way we sampled, we got, so the sampling algorithm gave us, sampling algo gave us X comma Y, sorry, not X comma Y. So Alice got X comma AX and Bob got Y comma BY. And we need to ensure that if there exists, so like no, rather we need to ensure the following strong property, that for all J in M minus I, because for revealed rows the property 2 is already trivially true because the precondition is not true. So for all J in M minus J, if AXJ is different from BXJ, sorry, BYJ, we need to ensure that xi, x, the ith row of x is different from, sorry, the jth row of x is different from the jth row of y. These are not. So what we want to prove, that we can sample an ax and by where we would have these properties with non-zero probability. So you want to show that probability that this happens, whatever this is, over that sampling algorithm which samples x comma y is strictly greater than 0. Okay, so but what are we going to do? We are going to prove something stronger. We will show that, so if you sample sum to x comma y from x tilde tilde, this is where we are going to sample from, right? For all unrevealed rows, j, xj is going to be not equal to yj. We'll show that this is non-zero. If this is satisfied, irrespective of whether axj is not equal to byj, then we are done, right? So no matter what ax and bx get, so if this is non-zero, then there exists x comma y such that xax and yby satisfy property 2. Sorry, so promise 2. So we now need to analyze this probability that all the unrevealed rows are different for x and y. So if we sample uniformly at random, what's the probability that they're going to be different? So yeah, this is what we want to do, and if we can show that this is going to be non-zero, we are done. So we'll start with one row. So let's say j is an unrevealed row. J is in M minus I. We know that average degree j of this x tilde tilde is at least 2 to the order log m, right? So what is 2 to the order log m? It's 2 to the some c log m. This is something like m to the c. Okay, so let's put C to be m square. Okay, so this says that average degree j of x tilde tilde is at least m square for every unrevealed row j. Now I want to understand this probability. So we would sample two matrices xy, actually xy uniformly at random from x tilde tilde, or actually even let's fix an x in x tilde tilde. And if you sample a y uniformly at random with repetition, y could be equal to x from x tilde tilde, what's the probability that xj is equal to yj? I claim that this probability is very low. And how low? This is at most 1 over the average degree j of xj, x tilde tilde. Okay, and if you believe me on this thing, then we can actually complete the proof. Then the proof says that so for any unrevealed row, probability j, if you sample x comma y, it's like sampling x and then sampling y. But no matter what x is, if you sample y uniformly at random, which is what we are doing, the probability that xj is equal to yj would be 1 over average degree, and we set average degree to be m square, so this would be at most 1 over m square. And by a union bound on all j in m minus I, we can get that the probability that there exists, so if you sample x comma y, there exists j in m minus I, where xj is equal to yj, is at most what? It's the number of unrevealed rows times this probability, right? So that's like the number of unrevealed rows is at most m, so that's like m over m square, that's like 1 over m. So the probability that there, if you sample two matrices uniformly at random, there is at least one equal row in the unrevealed rows is at most 1 over m. So with at least probability 1 minus 1 over m, you would get a matrix where all the you will get a pair of matrices x and y where all the unrevealed rows are different. So with non-zero probability, you will satisfy promise 2 also. But we need to prove this one, and this one is a simple fact. It's just by definition of average degree. If you think about it, what are we trying to do? So we have some matrix x. So we have some matrix x which is fixed from x tilde, and we have fixed on some row j, and this row is like maybe 0 1 0 0 0. We want to know what's the probability that a uniformly sampled y would have the same value, right? So if you think about it, so we are looking at what if y is sampled uniformly at random from x tilde tilde, what's the probability it will have the same row? Sorry, 0 1 0. Yeah, should have copied this. Yeah, these two rows are the same. So what's the probability of that? That's just like you can so whatever, so we can think of sampling y in two stages. First we will sample this partial matrix, right, without the jth entry, and then we will choose. So this is like first, so this sampling procedure can be done in two steps, right? First sample y minus j uniformly at random from x tilde tilde minus j, and then sample one of the neighbors of yj into what? X tilde tilde j, right? So to sample a complete matrix, you first uniformly sample a partial matrix and then complete it into the set x, right? You sample it from, so I'm just saying that to sample an edge, it is equivalent to saying that you had this bipartite graph view of x tilde tilde minus j and x tilde tilde j. So you just sample one of these nodes uniformly at random, and then it'll have some other, it'll have some edges coming out of it, and choose one of them uniformly at random. Every edge is an element in x tilde tilde. So now if you choose a a matrix like a matrix like this, on average a y minus j has average degree. So this on average is like average degree j of x tilde, right? So it has that many possible extension into the jth row. But since we have already fixed our x, only one of them is going to be favorable for us. So we are looking at an event where the jth row is the same as the jth row of x. So out of these choices, only one of them is going to be this one. So only one out of this one is going to be favorable for us. So this would say that intuitively the probability that you get the same row that you had in this fixed template x is at most 1 over average degree j of x. So this was an intuitive argument. I didn't do it very formally. So you'll have to, yeah, you have to do some more work to make it formal. So you have to like say that sampling a uniform edge is equivalent to first sampling a uniform vertex and then sampling an edge going out of it. But and this was for an average matrix. So yeah, so there's some more work here, but intuitively I hope you see this, right? So if I have a typical matrix y minus j, the number of possible extensions into the jth row is exactly average degree j of x tilde tilde. So the number of possible extensions is this. That's your universe, and out of that, only one of them is favorable. So the probability that you get exactly that one is at most this much. So this is what I claimed. Yeah. So I guess I'll stop here. I sorry for rushing through this last part. I just wanted to complete this whole argument in this week. Please ask me if you have any questions about this final argument. I'll hang around for how much ever you want. But let me stop here. Stop the recording.